So under the action of unit force, our system would reduce to this, as like we would be having a simply supported beam, that is this one here, with a force acting at its center, force of magnitude x1 is equal to a 1, like that. So under the action of this force, we know that the tension part of the bottom part of the beam would be caused to be under tension. Thus, a bending moment diagram would be drawn at the bottom. And then, since it is a simply supported beam under the action of a constructed load, it will have a triangular bending moment diagram, like this. And then the magnitude at the bottom, we know that it would be given by 1/4 Fp times L. But then our L is what? Is 2L. So this gives us 1/4 times Fp. That is, our Fp is the force which is of magnitude 1, x1 is equal to 1, then times the 2L. So we get our force as, we get our value for the bending moment as L/2. Then next, we come and look at the action of the original force Fp on the structure. Okay, so under the action of the unit force Fp, our bending moment diagram would still be similar to what we've just done for the action of the unit force. And then for that, we know that when the force pushes downwards, it will cause the tension part to be at the bottom. Thus, we shall be having a shape of that nature, isn't it? Then the magnitude would still be given by 1/4 Fp times the length of the beam, which is 2L. So this one here would reduce to what? Would reduce to a half. It would reduce to a half Fp, that is our force, then times the length, which is L, like that. So having drawn these two, now we move on and then solve for x1. But to solve for x1, know that we need to first of all calculate the delta 11 as the delta 1p. So of which the delta 11, our delta 11 would be given by 1/m1 integral 1/m1 over ei ds, then plus the integral of n1 over ea ds. So here we have the integral of the moment and then the integral of the unit forces. That is because under the action of the unit force, we do have an axial force x1 that still exists in this axial force member. Then under the action of the same force x1, we do have a moment that is created on the beam. So the delta 11 is got components of the moment and then the axial force. So we move on with the calculation. So this one here would be equal to, so the m1 we get it from this drawing here for the bending moment diagram due to the action of the unit force. So if I label this one here to be my m1, this is mp. So this one here would be equal to 1/ei, then into, now I have triangles, and then the triangles, I know that that it is part of the basic shape, but then as in like the entire triangle like this is not a basic shape, so I just divide it up into two, and then I form the right angle triangles which are of the basic shapes the other side, as you looked at when we were beginning this in chapter 5. So we get the area from that triangle, which would be a half, then times this base, which is L, then times the height, which is from here to here, that is L/2, and then now times our ds, or like what we were calling a y at some point, that is the distance at the center of gravity of the triangle from the base of the beam up to where we have the peak of that line. So we say that from this point up to this point we have a 2, over 3 of L, isn't it? So when you use similar triangles, you'll discover that this height y would be equivalent to 2 over 3 times L over 2, like that. Then there are how many triangles? There are 2 triangles, like that. Then we come and add 1 over EA. Then into our N1, we say that the axial force in this rod here is of magnitude 1, because it's the only force that we do have there acting on it. So it would be 1. It would be a 1 times 1, then times its length, which is L. So this one here would be giving us L. This one and this would be cancelling. This one and this would be cancelling. So we get 1 over 6. Okay, L cubed over 6 E I. Then plus from here we shall be getting L over EA. L over EA. Then remember that we have been given the relationship between what? Between the I and the A, in that I over A was equal to L squared over 10. So with that in mind, we shall be having this as this changes to 1 to L cubed over 6 EI, then plus this becomes L cubed over 10 EI, giving us an answer as 4 L cubed over EI. Then next we come and find our delta, our delta 1p. So the delta 1p would be equal to, that would be 1 over EI, then integral of that is m1 mp, then over m1 mp ds. And here we do not include the axial force, because here, like, we do not have on the mp diagram, like the mp is equal to 0, so there is no need for us to include the component of the axial force. So this would be equal to, as in like now from here, we say that we get the area from the mp, then the y we get it from the m1. So this would be giving us 1 over EI. So we look at the shapes which we have here. We have got a triangle, but then this is not a right angle. So to make it become a basic shape, we use a right angle triangle divided by into 2 right angle triangles which are equal. So likewise we do the same here at the point where they do have the peaks. So this gives us 2 similar triangles on both diagrams. So I can just choose one and then multiply by 2. So this would be the area from this one here. This would be a half times base, that would be a half FPL, then times the height, let's say that's the height, that is L, then times our y. So our y, now if I'm dealing with this triangle here for the area, I come to this triangle here for the y, so the y would still be at the same point at the center of the triangle here, that is at a length 2 over 3 of L, from this point up to this point here. So using similar triangles, we find that this height here y is given by 2 over 3 L, like that. Then times 2, because there are 2 triangles. So this gives us a value of FPL cubed over 6EI, like that. So knowing our delta 11 and then the delta 1p, next we come and what? We now come and solve for our x1. So x1, so from our equation, we have it that sigma 11 x1 plus delta 1p is supposed to be equal to 0. Therefore, here would be having 4L cubed over 15 EI this is supposed to be equivalent to negative, this is FPL cubed over 6EI. This, oh sorry, this one is times x1, therefore my x1 would be equivalent to, when you multiply, we shall be getting negative 5 over 8 FP for our x1. So after doing that, now we come and draw our bending moment diagram. And then to draw the bending moment diagram, we've got to have in mind the equations that for the sake of the axial force N, it would be equal to N1, that is from the action of the unit force diagram, then times the value of x1 that we found, then plus the value of the NP. Then besides that, for the bending moment, that would be given by M1 x1 plus the MP, like that. So let's see how we do merge up these two values on our diagrams. So now what we're going to be doing, let's begin by dealing with our axial force. So from this M1 drawing here, that is the drawing over here, this one here, we had an axial force that is given by x1 is equal to 1. So what we do, we are going to get that value of axial force that is a 1, then we multiply it by, so N would be equal to 1 times negative 5 over 8 FP. So we get our axial force as negative 5 over 8. We shall be getting here negative 5 over 8 FP. Then besides that, when you look at our MP drawing here, we do not have any axial force, so the value would be at 0. So when I add up a 0 plus negative 5 over 8 FP, I'll be having my axial force as a negative. My axial force would be given by negative 5 over 8 FP, like that. Then after that, now we come and look at the moments. So the moments from the M1 diagram have, I get the value of L over 2 as the moment, then I multiply it by what? Negative 5 over 8. So when I do that, I would be getting a value of what? A value of negative 5 over 16 FPL. That is a negative. So since it's negative, that means it's now supposed to be existing on this. It is supposed to be lying on this upper side, of the drawing, like that. So here we shall be having 5 over 16 FPL, like that. Yeah, so it becomes a positive because you're now drawing it on the opposite side. Now to come up with my final value of the moment, I now get the 5 over 16 and I subtract a half from it. Let's see what we get from that. 5 over 16 minus a half. We do get negative 3 over 16. So negative 3 over 16, that means our bending moment diagram remains on the lower side. So let me use a different color. So that means that now we come and draw it somewhere here, like that. This is negative 3 over 16 FPL for the moment. So this one here becomes our final internal force diagram. So that is how we deal with the composite structures. Thank you.